And I would like to quickly introduce our next speaker, Professor Erdal Kayacan. He is the Associate Professor at the Department of Electrical and Computer Engineering and the Director of Artificial Intelligence in Robotics Lab at Aarhus University. Today, she will be talking about future of smaller, faster, more agile, yet safer aerial robots. So, Professor Kayacan.
Thanks for the kind introduction. I will talk about future of smaller and faster and agile robots for possible applications in the future. Autonomous drone racing has recently caught attention in robotics community. We know these races from Aarhus conferences in the past. The long-term goal is to have autonomous UAVs that can fly as well as or even better than the skilled human pilot. Better means faster and safer in this context. It's a problem of agile robotics as the performance of the drone must push the boundaries in terms of perception and autonomy. This problem is also a suitable benchmark problem to demonstrate perception, planning, and control algorithms, as it requires accurate, robust, and computationally efficient algorithms with multidimensional signals. Is it a game? Of course, it's not a game only. We think that the technologies which are developed for the autonomous drone racing problem can be transferred to other domains, such as looking for people under collapsed buildings after an earthquake, or maybe mining operations. All these operation domains require fast and reliable perception, planning, navigation, and control algorithms. There are some other state-of-the-art methods in the literature. Some of them use conventional computer vision algorithms. They tend to fail in complex backgrounds and illumination changes and occlusion. There are some also deep neural network methods which have millions of parameters in the literature. Some hybrid methods are in the literature as well. A method is segmenting 4 corners and use a deep neural network to associate them to a gate. And there are also end-to-end planning methods. And as we all know, these methods work well when you are lucky. Somehow you design it very well. But when there is a problem, it's really difficult to find the problem in your code. Unlike the standard object detectors, which predicts gates locations in the image plane, our method unifies prediction of center, orientation, and distance of the gates in a single deep neural network. And in this application, we are using a fisheye lens. Our motivation is that in real life, the obstacles are closer to each other, and fisheye lens is giving us more field of view. So the network is implemented as a convolutional neural network with 6 convolutional layers and a single fully connected layer at the end. The convolutional layers extract features from an input image, and fully connected layer predicts the confidence values. The output layer is inspired by YOLO object detection network with relatively low number of parameters, which allows us to achieve high inference frequency. To train and benchmark the network, we introduced a new large-scale dataset, namely AUDR dataset, that addresses different scene appearances in gate detection problem in the context of autonomous drone racing. The dataset contains labeled images according to gate layouts, including single gates, multiple gates, occluded gates, partially visible gates, 2 closed gates, and 2 far gates, as we see on the bottom right of the screen. The ground truth information is provided using an accurate motion capture system, although we know there are some other methods in the literature as well. And the dataset is publicly available for interested researchers. For benchmarking, we have trained our network called GATENET and some recent state-of-the-art baseline methods in the literature in our dataset, namely AUDR dataset. As we can see from the table, GATENET is superior in gate distance prediction compared to other baseline methods. and it has better performance for gate orientation prediction in challenging cases, for example, partially observable gates, or when they are pretty close to the camera, which is actually the main motivation of using a fisheye lens. In our experiments that you see on the video on the left side of the screen, the drone completes a racetrack with multiple gates where the gates are pretty close to each other. In this application, it's around 4 to 4.5 meters. And our speed is around from 2 to 5 meters per second. GATENET is also robust to background perturbations of human movements or also gate piece disturbances. It can also handle position and orientation changes between each lap. So it's robust with orientation changes as the gate will appear smaller in the image plane at high yaw angles. So another work that we have done in this area is PENCILNET. It's a trial to sim-to-real transfer learning for autonomous drone racing. So our motivation is that the labeling of a data and collecting the real-time data is difficult in real time. So we propose zero-shot sim-to-real transfer learning. And then it will be robust to illumination changes with the help of PENCILNET. So obtaining real-time data with accurate ground truth labeling is difficult and costly. And it's really difficult in real life. So the generating data from simulation is a preferable approach, but we need to think, or we need to address the sim-to-real gap as even a photorealistic simulator such as AirSim. Perception can fail due to lack of noise and poor data representation. So in this work, we employ a smart input representation named a pencil filter to abstract the surrounding information so that it can generalize and learn perception tasks better. In our experiments, the drone completes different race tracks with varying gate layouts and lighting conditions such as daylight and night light with different illumination. So we can see that the proposed network is robust to light variations, and it's more robust when compared to the previous work in the literature. I must also, of course, make sure that we are not using any motion capture system in this application, and everything is on board. The last work that I'm going to talk about is the event-based vision for autonomous drone racing. In this work, we have designed a novel deep neural network based gate detection method for autonomous drone racing. So in this method, based on the gated recurrent units, utilizing sparse convolutions for detecting gates is proposed with the help of event-based camera for autonomous drone racing. Throughout the experiments, we showed that the event-based vision with the proposed gate recurrent unit and pre-trained models on simulated event data significantly improves the gate detection precision. Furthermore, an event-based drone racing dataset consisting of both simulated and real-time data is also publicly released in our GitHub page. We use a lightweight variation of the VGG11 network as a backbone feature extractor and add a gated recurrent unit before YOLO-like output regression head. The motivation is to capture the temporal information from arriving event sequences. Collecting and annotating data from a real-time event-based camera is also very challenging, and it's an expensive process, and it's also time-consuming. So this work aims to reduce the use of real event data by generating event data from simulations. So we first pre-train the backbone network or the feature extractor and the output regression head using only simulation data and fine-tune it with a small real-time data as transfer learning allows us to do. Compared to state-of-the-art methods, the method that we propose has a significant improvement in average precision of all real data sequences across different illumination settings. That all we know, working under different illumination is one of the best features or skills of event-based cameras. In the real-time video on the left-hand side of the screen, in the first part of the experiment, as you see in the video, the gate detection task is demonstrated in difficult conditions. So in order to create similar conditions in drone racing, the drone is rotated with a very fast speed, yaw speed, and we vary the lighting conditions. As you see, the drone is rotated around its yaw axis up to 3 radians per second. And while we are doing it, we are changing the illumination in the video. Actually, the illumination changes in the video is more significant than you see in these videos, because somehow we are using GoPro cameras and these cameras are adjusting the light. So in real life, these changes are more significant, I can say. The main reason that the performance degrades is that the event-based camera returns more noisy data when it is too fast or too slow. So also the network of the input becomes less sparse when it is rotating very slow, and it results a slower response in an event-based camera. So it seems that there is an optimal speed for an event-based camera. And in the second part of the video, the drone is completing a full autonomous drone racing track using only event-based camera. So the task is autonomously navigate through multiple gates in our racetrack. And we are using a single event-based onboard camera with image-based linear control methods. So thanks to the accuracy of the gate detection, the drone mostly tracks the gate center and it can successfully pass the gates with a reasonable accuracy. Of course, the scenario that we are showing here is pretty simple because the drone is seeing only one gate at a certain time and it's moving relatively slow. So in the future, we are planning to work with multiple gates as a single image in the drone racing context. Our conclusion is that for autonomous drone racing, the perception, planning, and navigation blocks are coupled in autonomous drone racing, and it's a pretty difficult robotics problem because if one of the blocks fails, the overall application will fail in your scenario. And event-based vision is promising. I can say it's a little bit premature technology, but it's promising because it's robust to motion blur. I can say even there is no motion blur in this case. And it's very robust to illumination changes. Well, we haven't done it yet, but maybe in the future, instead of using event-based camera for using only event-based camera on board, another application could be to use an RGB camera and an event-based camera together to enrich the skills and robustness of the RGB camera. We believe that this is a promising direction. This is because when we are out of the lab, most of the applications don't have perfect working conditions. Just imagine a mining operation that you can't control the environment's illumination, and then you are trying to fly as fast as possible. So in these applications, you need to fly pretty fast, but only using an RGB camera may not be enough. Also, last but not least, in autonomous driving applications, we believe this type of camera can be extremely helpful, as it can detect the moving objects much faster than the RGB images. That means it will make autonomous driving safer. Imagine that there is a pedestrian, or there is another car just jumps in front of the car, and there is a processing time when you use an RGB camera. But with event-based vision, it will be very fast, and you will detect the future trajectory of the object, and then you can avoid any accidents in the context of autonomous driving. Thanks a lot for the time, and I'm looking forward to getting your questions.
Thank you, Professor Kayacan, for giving us this amazing presentation. And now we would like to collect questions from the audience and the online participants.
Thank you very much for your presentation. My question is about, mainly I'd like to get your opinion about, the which approach do you think is more suitable to improve the capabilities of autonomous drone racing compared to skilled human pilots? Is it the conventional, approach where you have modular system that consists of control modules, navigation modules, or the new methods that try to use deep learning or artificial intelligence to combine all these approaches? Thank you.
Okay. I feel a little bit confusion in this question because when we say conventional methods and deep neural network methods, we mostly talk about perception. So you can use traditional object detection methods in computer vision, or you can use deep learning methods for object detection. But I think you also referred to different blocks for navigation, perception, and planning, and its alternative, it's not deep neural network, but I think its alternative is end-to-end planning methods, where the input is the raw data from your sensors and the output is the actions of the robot. So now, as a response to your question, I will come back to the first group, that we are using either computer vision methods, traditional computer vision methods, or deep neural network methods. So my response is definitely deep learning methods. This is because when I don't fix the shape, color, and geometry of the gate, deep neural network methods has significantly better skills than the traditional computer vision methods. Plus, when there is a background change and when there is illumination changes, all these in all the aspects of robustness, deep neural network methods definitely work better than the traditional methods. The second part of the question is the end-to-end planning methods. In the context of drone racing, it's really challenging because you are training this network with huge amount of data, and it's really challenging to design end-to-end planning methods for drone racing because the environment is pretty complex and the background is pretty complex. You should be a bit lucky. If it works, it works. If it doesn't work, I mean, you are starting everything all over again. So end-to-end planning methods may work or may not work in this context, but I haven't used them in the context of autonomous drone racing. Did I answer your question?
Yes, thank you very much.
Thanks.
Thank you, Professor Kayacan, for your presentation. My name is Eric Ferron, and I had a question regarding the tactics of racing. I get from your presentation lots of views for one gate, but to what extent you plan the race with like several gates ahead of time, and to what extent being able to see several gates at once influence the way you're going to detect them on the one hand, and then take advantage of their relative positioning on the other hand.
If I understand your question correctly, you're asking what will happen when we see multiple gates at a certain time. Do I understand correctly?
And how you take advantage of that.
Okay, great. Actually, in the first half of the presentation, there are cases that we see more than one gate. So my comment about a single gate assumption is just for the last part of the presentation, where we use event-based vision. So for the RGB camera, we have tested the network with 2 gates appearing in the same image plane. And what we do is we are detecting 2 gates simultaneously, and we are telling drone to pass the first gate first. So this is not a big problem for the RGB camera because the algorithms are a little bit more mature for the RGB camera. For the event-based camera, it's a little bit more challenging. So we haven't tested yet, but I'm sure in the couple of years, they will test it in the full context of autonomous drone racing when you have more than one gate in the image. So we have multiple gates in the first part of the presentation and only single gate in the second half of the presentation. And the second question of yours is, how do we use its advantage? Or did I answer the second part of the question?
Again, so it was, how do you take advantage of when you race the knowledge of the position of several gates ahead of time?
Oh, great. Actually, of course, when the race is planned in a way that you're seeing more than one gates, of course, it's going to be more challenging. But the advantage could be to plan better, because if I see several gates in the image, and if I can detect where they are and what is my distance to the gate, right, relative to the drone, then I can make a better, more smarter planning methods, use planning methods, and then I can even change my speed over the time, right? So that could be, of course, better when compared to detecting only one gate in the track.
Thank you.
Hello, thank you for your talk. This is Alberto Quattrini, and I have a question on what do you think the drone racing, how can it help to, in a way, drone autonomously navigate in real-world environments? Because drone racing is relatively constrained, right? So you have the drones that go through the gates. And so in a way, the perception system has to detect the gates. But in a structured environments, you don't have, right? So such sort of landmarks.
I think the main motivation is to benchmark the perception and control and planning methods in a single robotics problem, that the speed is important and the efficiency of the algorithms is important. And also the latency from the sensors and from the algorithms is also important. So it's one of the best benchmark robotic problems in the literature. How can it help in real world applications? So we believe that these perception algorithms, fast algorithms with low latency, that can help in real world applications in a way that you need to complete the task as fast as possible. This is because, as you know, the main problem in the autonomous robots is the battery life. For a drone, it's around 10-15 minutes for a small size drone. And when you send these drones to somewhere, you can't increase the size of the battery and flight time. So the best thing you can do is that you need to finalize your task as fast as possible and as accurate as possible. And then, yes, there are not landmarks in most of the real applications, but we can design the environment maybe with these landmarks in the future. For example, like mining, right? So maybe we can put some landmarks in mining environment just for the drones to detect them. But I think first half of the motivation is a little bit more significant in the robotics community, that allows us to test control, planning, and perception together, and the efficacy and efficiency of the methods is really important and critical not to fail in the overall task.
Thank you.
It looks like we have already covered all questions. Thank you, Professor, for your detailed explanation for our questions.
Thanks a lot.